Hi, my name is Yashwanth, and I'm a research scholar in Center for Interdisciplinary Programs at IIT Hyderabad. My research proposal is titled Manifold Constrained Learning for UAV Dynamics and Control. My PhD is funded by the Ministry of Education, and I currently hold a CGPA of 9.58. Prior to joining PhD, I have completed my MTech in Thermofluid Engineering at IIT Hyderabad with a CGPA of 9.57. During the first year of my PhD, I have published a conference paper and obtained a patent. My PhD is jointly supervised by Dr. Vishnu Rajasekaran Unni from the Department of Mechanical and Aerospace Engineering and Dr. Nityanandan Kanagaraj from the Department of Physics. The motivation for my study comes from the fundamental difficulty in modeling small multi-rotor and flapping wing UAVs, which are sensitive to disturbances, as they generally operate in highly unsteady and nonlinear flight regimes. Hence, there is a necessity to utilize standardized data-driven methodologies for performing system identification on such UAVs and also developing control systems for the same. But in utilizing these data-driven methodologies, there are a few key challenges. First is the large number of system variables, which leads to the known curse of dimensionality. Second is the large number of samples required during training, which leads to increased sample complexity. Hence, we propose a fundamental question here. Can we address these limitations by performing system identification over a more focused operating range of system variables? Or in other words, can we introduce physically meaningful constraints on the motion of the UAV such that performing system identification still captures the key dynamics? Hence, we propose to adopt a hardware-in-loop-based approach for performing this system identification, which involves first developing a training rig that introduces geometric and kinematic constraints as well as symmetries, which we can leverage to reduce the learning complexity. Now, such a training rig allows us to repeatedly test and collect quality data for different input conditions. Once we learn the dynamics in the constrained training rig, we aim to develop machine learning based approach that can transfer the learned dynamics to the unconstrained environment, which corresponds to learning the complete dynamics in the free flight. In order to realize this proposed framework, there are few critical challenges. The first is designing and developing a robust training rig that introduces these constraints. Second is deriving a mathematical model of the training rig that describes the nature of the constraints. Third is to develop instrumentation to reliably acquire data for our training requirements. Towards that end, I have designed and developed a 5-degree of freedom training rig that introduces the constraint to an UAV. Second is to derive, and I've derived a mathematical model for the training rig using Lagrangian mechanics and successfully implemented the instrumentations and started collecting the data for our training requirements. To summarize the proposed research, I have first addressed the critical challenges pertaining to design and developing and mathematically modeling the training rig, and I am underway for validating the analytical model and acquiring extensive training data. In the next phase, we begin with learning the dynamics of UAV in the constrained training rig setting, followed by developing methodologies to transfer this learning from constrained to unconstrained setting, and finally, evaluate the implications of using control algorithms or synthesizing control in using the transferred learning. The expected outcome of my PhD would be a rigorous systematic framework for manifold constrained learning of UAV dynamics and control that is sample efficient and robust. Thank you.